Hello, welcome to Calculus 3, Math 253 here at Cañada College. My name is Lapuz and I'm the instructor for the course. In this video we will take a look at section 6.8, the divergence theorem. This theorem is sometimes known as Gauss's theorem, and the divergence theorem relates a flux of a vector field with a triple integral. Now the triple integral is actually computing the div of that vector field, which, remember, the div makes a vector field into a scalar function, and so we're taking the triple integral of that scalar function and then replacing it with a flux integral, or vice versa, depending on which is going to be easier. But the words that we would normally use to try to relate this to the fundamental theorem of calculus would be taking the integral of a derivative of a vector field, and that's over a particular solid region E, and that's going to get replaced with one less integral of the original function over S, which is the boundary of the solid that we're looking at. So S is going to have to be a closed surface that's going to cover or encompass your region, your three-dimensional region E. And then you're going from a div to the original function. All right, so that's Gauss's theorem. Let's take a look at the geometry of Gauss. So in the triple integral, you're looking at a solid, and each of these solids, solid can be broken up into sub-cubes or boxes, and then for each of these boxes what we can do is we can measure the div, what's happening going outward out of these boxes. And so as you're measuring each of these boxes side by side, stacked on top of each other, and measuring the outward component, that eventually has an effect on the surface of your region. In the surface of your region, you're actually measuring now the actual vector field going outward from the region, and so that measures the flux. And so that's kind of like the geometry motivation to take a look at what's happening in Gauss's theorem. Now let's, aside from computing each of these sides of the integral and showing that they're equal, one of them might be easier than the other, as we'll see. So let's take a look at how to apply Gauss's theorem. Gauss's theorem, again, it's the triple integral of a div over a solid region is going to be equal to the flux integral of the original function over its boundary, and the boundary has to be a closed boundary, and sometimes we use these circles around the integral to say that we're integrating over some closed region, in this case a closed surface. So let's take a look at an example where we would integrate a flux integral over a box. Now this box has 6 sides to it, so if you're going to do a flux integral through this box, then you're going to have 6 integrals. And so instead of computing throughout these 6 integrals, what we might do is just do a triple integral over a box, which is fairly easy because in rectangular coordinates that box is just going to have constant limits for all the variables. And so that might be easier to do than having 6 flux integrals. And furthermore, taking the div of a vector field, you're taking the derivative of a vector field, which simplifies your vector field even more. So in this case, it would be beneficial to start to be given a problem to find the flux through a 6-sided object, and expressing that solid as just one solid, then doing the triple integral will definitely be a lot easier. Another way to use Gauss's theorem is, for example, if you have the surface that's open, well, you can't use Gauss's theorem on an open surface. So let's see how we can, I mean, we can't use it directly, but let's see how we can skirt around using Gauss theorem for an open surface. So in this case, let's say you want to find the flux through this through the surface of a cone, and the original function or the vector field that you're taking the flux of might be complicated. And so let's see if we can use Gauss's theorem. This is an open surface, so it doesn't have an enclosed region, but what if we cover it up and enclose the region? So we cover it up with a disk on top. Then we can use Gauss, because now it has an enclosed region. We can find out the triple integral within that region. But as we do that, if we want to find the triple integral over that region, remember that we also added the top part, and so we should remember to subtract out the flux of the top part, which in some cases, because it's flat, then the flux going through the surface might be easier to compute than the flux going through the original cone. So there's a lot of tricks and things to consider when you're using Gauss's theorem, or even Stokes' theorem for that matter. And it kind of depends on your situation. It depends on the surface or the region. It depends on the vector field, to see if it's a complicated vector field, if the div of that vector field would make it easier to do or to deal with. And so again, it's going to require some practice, some different scenarios, and hopefully you get to see that in the checkpoints and in the homework problems. Okay, this is our last section, and so we will close with one more overview of all the big theorems after we do this. Meanwhile, good luck with this section, and good luck with the final exam.